Then I will start my clock.
Okay, good morning to my colleagues here in the US in Binghamton and other parts of the country, and good evening to my colleagues in India at Vellore Institute of Technology, and to our speaker who is joining us all the way from Italy. On behalf of Binghamton University and VIT, we are delighted to welcome you to this joint webinar series. This is a joint effort between Binghamton University and VIT. And today we are delighted to have our fourth speaker. Today's speaker is Dr. Bruno Diaguano, who is a physicist, and his research interests include the development of models, algorithms for the design of a number of things, such as nanostructured materials, simple and complex fluids, and polymeric membranes. Also innovative systems for energy storage, thermal and compressed air energy storage, and PEM and regenerative fuel cells, as well as heliostat fields of concentrated solar power applications. Currently, Dr. Bruno is a visiting professor at VIT Vellore, and he acts as a scientific advisor and consultant for international institutions. Prior to that, Dr. Bruno was a scientific director of the CIC Energíon in Spain, and the director of the Renewable Energy Program of CRS4 in Italy, and a temporary assistant professor at the physics department at the Constance University in Germany, and scientific employee at the condensed matter department of the Free University of Berlin, Germany. Dr. Bruno is an author of scientific monographs, review and research papers, and he's very active in promoting European and international research projects and renewable energy scenarios for a better life. So I'm very honored to introduce Dr. Bruno to join us to deliver this seminar. And in case you did not hear the conversation before the seminar started, Dr. Bruno is actually currently in Italy. So we are very delighted to have him. And Dr. Bruno, I will turn it over to you. Thank you.
Okay. Thanks a lot for the introduction. And of course, thanks a lot to all people that were inviting me to this series of seminars. Now, today, I will introduce you into the field of thermal energy storage, more in particular, about now the new materials that are going to be used in this field. And I will say more specifically about the structural and thermal properties of these new materials that are nanomaterials. So there, I will not spend many words, I will not spend words at all about introducing CNR. Already people were introducing VIT. VIT was already introduced by other speakers. I will also not spend words to introduce CNR. CNR will be introduced by Nirmala Grace, since she's the director of this research center. But I want to point out just one thing, that the things that I'm going to show to you today are the results of, we can say, of a research group that is really delocalized in the world. So then to the things that I'm showing to you, were contributing people from the UK, people from Italy, then people from India, and here you have a list of the people that were contributing to this. And Andrea Flores, that is professor at the University of Lincoln, Leonardi, that is researcher at the CRS4 in Sardinia, then people from India, of course, my PhD students, that is Sankadip Bose, and one of my master students, that was Divash, then also other scientists, Mani Kartik, that is a senior scientist at this ANCI department in India also, then of course Nirmala was contributing. So then also there are now the group is growing, and then in this group, new collaborator will come. So mainly just to stay also linked with something that is happening in the US. Now within this group will come also Norman Wagner, that is a professor at the University of Delaware. That is not that far, we can say, relatively not that far from Binghamton University. And also other people will join this. This is one example of, we can say, of situation in which now, instead of moving physically, the researcher, we are moving the scientific ideas, scientific research activities. And then you see that in the COVID time, maybe this is the best thing. Let's move, let's allow the sharing of the ideas, and the people can stay, can contribute to the group activities by staying there on location. So there, now after this node, let's go really to the structure of the talk of today. So then I will, first of all, I will present to you a small introduction about technological application. This is just to show what are the technological motivation, the industrial motivations that are behind this kind of application. And also then I will do something about we can say the scientific motivation to approach the thermal energy storage with nanomaterials. Then there will be a very, very short review about the experimental technique, about experimental results, and then I will go through, we can say, more the theoretical aspect about the simulation, and I will show to you how then the simulation can be performed and how then the simulation results can be used really. And then I will say at the end, in the conclusion, really to set up design criteria for new materials that can be relevant in such kind of field. So then let's go to this, we can say, to the technological motivation. You see that I will show to you just one particular kind of application of we can say, of storage, of heat storage material, but the particular application that refer to application at very high temperature, in situation in which you have to store a lot of thermal energy at very high temperature. For example, you see the Planta Solar de Cerro Dominador that is in the Atacama Desert in Chile. So then you see that this is it's an industrial application, there is a commercial application, but then you see that in order to allow the production of energy 24 hours a day, but only the source of energy is provided by the sun that is not shining 24 hours a day, you need the storage of the heat that you are collecting during the day, and then you need some storage devices, storage tank, and a fluid, a system, material in which to store the thermal energy. In this case, is a molten salt, and then you see that also is used as heat transfer fluid. This molten salt, and this molten salt are usually a mixture of sodium and potassium nitrates. And then you see that also now in our days, the electricity that is produced, but is reaching really a price that is really competitive with the price of the electricity that is produced by conventional non-renewable energy sources. But there, let's go. Of course, also in the States, you have such kind of application. Then I am just putting just one, but there are many. The one that is now is already active, that is in the Ivanpah installation that is in the California desert. And you see how big is this installation. that is something like 392 megawatt in power, and also you see the extension of this thing, And now you see that this is an heliostat field in which we can say the sun radiation is collected by the fields, and then is sent to the end point that is at the top of the tower. So then somehow we can say in the solar field, just photons are moving, something that is immaterial, like the example they were saying, let's allow scientific idea to move and not physical researcher. But then you see, but there are so many other applications. But while this is from one application in Spain, that one of the first applications that is Andasol project, power plant, okay, is this one, in which now you see that the collector is a parabolic 12, and in which now there is a receiver tube, and then through all the field is something, and its transport fluid is moved, something physically. But now you see the difference in these two things. In one case, more physical material is moving, in the other one, just photons are moving. But in any case, in both, there is a storage, thermal storage. Now for this, we have a little bit more detailed data, and you see some data about the characteristic, the physical property of the storage material, that is this solar salt, a combination of sodium, 60% potassium nitrate, and we have a specific capacity that is 1.5 joule per gram per degree. And you see, this is a relatively small application, but then you see how many tons of storage material we need. And also you see there, what is the delta T of temperature that is used in this kind of application, that goes from 292 goes to 384 Celsius degree, and these are a limitation imposed by the stability of the high temperature is imposed by the stability of the storage material. The low temperature is due to the fact that now otherwise the salt will freeze. So then let's go. But then you see that to have a real deployment of this, you have really to lower the price of the electricity that is produced. And now I am also speaking also to people that stay in the States. So let's see something, some goals from the Department of Energy of US. And you see that we can say there is this sunshot initiatives of the DOE that says, okay, we have really to lower down the electricity, and there are the goal for the, I am going in the wrong direction. How to go? Okay, so then you see that one has to reach this lower price. To reach this lower price, now the key factor is really to reduce the cost of the storage. To reduce the cost of storage, you need material with better properties. First of all, you need materials that will be stable in a larger temperature interval. So we saw that this was for sure lower than 800 degrees, but now the target, let's produce material that's stable above 800 degrees Celsius, but this is a target, stretch target is above 1000, because in this way you can really fully exploit all the concentration ability of the tower system. But the other thing that is extremely important is also, I was saying that the CP of the solar salt is 1.5 joule, etc. But now the target, we have to go beyond this value, and the stretch target is something larger than 3.75. Remember that the one of the water is 4.08, something like this. So then, one has to reach this target if one wants really to have a future in which now this technology, together with others, are used to build the world based on renewable energy. So, but then this where the technological motivation and the number of power plants that are being constructed in the world is really increasing and increasing. And now, for example, China is starting to take the lead. And in the years before, was Spain and the US that were driving, we can say, the development of this CSP application. But now, why we are thinking that we can somehow try to reach these goals that have been written down by the DOE? The reason is that also scientific is a new paradigm is emerging. It's a paradigm that says that now nanostructuring can really expand the thermal limit of known bulk material. So why this? Why we are thinking, the scientific community, not me only, the scientific community is thinking that nanostructuring can really expand the thermal limit of known bulk material. The reason that is behind this is due to the fact that in nanomaterial or nanostructured material, the amount of interfaces that you have in your material is really a huge really big. So then in this table you see in a bulk material, take a cubic centimeter of gold, for example. The external surface of this one gram of gold would be something like 0.72 square centimeter. But look now, in nanostructured materials, you can have in 1 gram, for example, of a carbon foam that is a nanostructured material, you can have an interface area that is 8 orders of magnitude larger than this. So then the physics of this nanomaterial, nanostructured material, will be dominated by the interface properties and not by bulk properties. So then a new physical behavior is emerging for this kind of material. And then we are trying to do research in this field because thermal property of interface, we believe are strongly different. We know already a little bit about this, are strongly different from those of the bulk. And we are thinking that the difference is in a positive direction, that the thermal properties are better than the bulk material. So, but then, what is the mechanism that we want to use to store this thermal energy? We have here in this table, we say that to store thermal energy, you can store them in 3 different ways. Essentially, as a sensible heat, you give energy to your system, and your system is answering by increasing its temperature. You can store as a latent heat. You give energy to your system, and your system is making a phase transition there. It's storing a lot of thermal energy. So you give energy to your system, and then the energy is stored by performing, we can say, chemical reactions. And then in this case, the density of energy that you are storing is even larger. Unfortunately, I mean, the one that are more close to the application, more developed, is the one in sensible heat, and now also latent heat is becoming something that is approaching more technological application. And then you see in this table the role of nanomaterials, and we can say nanostructured materials. You can have nanofluid. Nanofluid means nanoparticle, for example, in water, nanoparticle in molten salt, so that you can have carbon foam, like this other case, in which you, in the foam, you insert, for example, one other material that will perform a phase transition in the temperature interval of specific of your application. Now today we will just concentrate on, we can say, on sensible heat via nanomaterials. Okay, what is a nanofluid and nanomaterial? First of all, is nanofluids is a modern word. It's a modern word for something that is very old. That means for a colloidal suspension, for colloids that are very well known, at least in the range of room temperature. And now I want to stress to you the word stable. I mean, the nanofluid has to be a stable colloidal suspension. And now you see for the kind of these applications, we can have the liquid dispersion medium. So that means the suspending medium, it can be, so these nitrates, you can have mixture of them, can be carbonates or mixture of carbonates, you can have mixture of halides with sodium chloride, sodium fluoride, etc., etc. And that's instead of suspending medium, so they mean the colloidal particle or the nanoparticle, you can have silica, alumina, titanium, and those other materials. And then usually in the application, they are using in general nanosphere, the spherical object, and then with a dimension that is usually going from 2 to 200 nanometers. And what is also something that you have to notice, that the weight percentage of the nanoparticle that you are adding to your suspending medium is a very, very small amount, something that is 0.5 till 5%. But although this, we are claiming that you can really, really improve by a lot the thermal properties of the bulk material. In the case, the bulk material is the suspending material. So then the mixture, the nanomaterial will have, we are claiming the strong indication that will have property much better than the mixture of the pure salt, molten salt, or of this nitrate, etc., etc. But then let's see, there are indications, but let's see what is, I will just try I will summarize it just in one slide, all the experimental results that have been produced in this field. Looking at the bottom of this page, you see that there were already many review papers have been published, and then you see the number of papers that were reviewed by the reviewer writing this report. To summarize, I am also showing just two pictures. Then there is the specific, the first one on the left, top left is just the specific variation for carbonates in which there are nanoparticles inside. And you see, according to different researcher group, and also you see that from left to right, then the nanoparticle size is increasing. You see that there is a strong variation, we can say, on the enhancement of the heat capacity that you can have in the mixture with respect to the heat capacity of the suspending medium. In this other picture, even the situation is really complete. It's also it is a strange, let's say a strange situation, in which now you have a nanoparticle in this sodium and potassium nitrates that are used as base, as the suspending media. But you see the situation is even worse than the other case, in which some researchers are finding enhancements, some other researchers are finding that there is instead a decrease. So there are, I mean, all the reviewers are pointing out that there are inconsistencies in this data. So I want just to read, there are some reports of discrepancies between the results reported by different studies using the same material. So there is really, we can say, a non-clear situation from the experimental point of view. And due to this fact, also the experimentalists have difficulties in interpreting their data, essentially because a molecular theory explaining all this effect of the specific heat does not yet exist. So then this is giving to also motivation to do something more theoretically. So But why the situation is this experimental? What we can say, how we can improve the experimental situation. Now there are some issues that you can do, some challenging problems that you can open. So that one has to go beyond all these experimental data have been measured by just using one experimental technique. Maybe it's better to use more than one experimental technique. Then also by using, one has to use more data to produce more data to understand if in the suspension that you are doing, there is the phenomenon of agglomeration or aggregation is present, because then you see this here, I mean, this can be measured by using the DLS diffraction light scattering experiments, and then you see alumina in water, and then you see if 1D is the nominal size of the particle that you are putting in your suspension, then you see that there are instead agglomerates in your suspension, but they can destabilize your suspension. And the situation is even worse, but now, just now, they are producing such kind of results. 2019, last year, we can say, in which also they are trying to do the same thing in the case of, for example, silica in the solar salt. And you see that the silica and the solar salt is really producing very large agglomerates that are making, I mean, the agglomerates are precipitating, then you get just two phases, but then, I mean, you cannot make any sensible, this is not anymore a stable colloidal suspension. So then one has to really change this state of affair from the experimental point of view. This means that to change this, one has to develop stabilizer of this new particle that you can attach, that you can use to functionalize your particle in order to get stable suspension, especially at very high temperature. But I want to say that, I mean, the science to stabilize colloidal suspension is very well known for the case of room temperature, in which you can add some surfactant on the particle, but surfactant are stable at a low temperature. At a very high temperature, the chemistry of functionalizing the surface is largely unknown. So a lot of effort has to be done in the scientific community in order to stabilize this suspension at very high T. But also from the simulation point of view, since there is not here, is something has to do. So there is a need of theoretical and simulation approaches. And as we can say, the first thing one has to construct is still lacking, but now I will show how you can easily do this thing. It's still lacking a chemical physics approach to nanoparticles, especially that the nanoparticles are non-homogeneous liquid mixture, as with respect to, for example, instead, a lot is known for, of course, for the solution in which you use the Raoult law, the Henry law, to understand the behavior of the suspension in the dilute regime. And so then also you use the Henry law, especially Henry law, to define what is the dilute regime. So Raoult law is showing the ideal behavior of a law of an homogeneous liquid mixture. Then the Henry law is saying, okay, there are some solutions in which they are not ideal, but still there is a regime in which the properties of the suspension are changing linearly. And this defines, we can say, a dilution limit of your system. So, and this is, we remember that in all these experimental results, the concentration of nanoparticles is very low, essentially stays in this dilute regime. But then also you have to develop some, we can say, simulation approach in order to understand the mechanisms that can stay behind this kind of behavior of the heat capacity. So then here you see that you have to model to make some molecular dynamic simulation by inserting your nanoparticle inside the solution. Then you have somehow to see the results of all the configuration, that the trajectory that are you generating with the molecular dynamics. A very short review of how we can not review. I will just show how we can construct. We can say this chemical physics theory to explain the behavior of the of these nanofluids. So then, to do this, you can imagine your system is made by 3 components. So this is the nanoparticle, the base suspending fluid, and now you say, since there are interfaces, there is an interface region that is contributing to this. So this is, this is all the things that you need. Then you can manipulate a little bit the equation, but then you can say that the Cp of the nanomaterial is due to the Cp of the ideal solution, suspension, and here you have, this is the ideal term, is simply the sum, the weighted sum of the Cp of the constituent, that means of the nanoparticle, the suspending material, plus an excess term. So that's the way in which physics is constructed whenever there is a deviation from the ideal behavior. And so here you have the definition of this excess term. Remember that this, due to this definition, this Cp is just an excess term, is not a true heat capacity, because then this expression can be positive or negative, but instead, of course, you know that heat capacity are always positive. By continuing to manipulate it, then you can get the expression of this, or quasi etc. But then you can do also very simplified and a little bit more simplified approach in which you are introducing the specific nanoparticle surface contribution to, and then via this, then you can define the excess term in this way. Then you have the excess term in which you have this quantity that will depend just from the temperature, and the dependence on the, we can say, of the nanoparticle properties are outside, are made explicit in this term. There is the sigma, the diameter of the nanoparticle, and the density of the nanoparticle. So then we have an expression that we can say, and you already can imagine this expression is like, corresponds really to the Henry law that is used for the solutions. So, but then if we can evaluate all the quantities that are appearing in this expression here, also here, we will not use this because it's more complex due to the evaluation of terms like the thickness of the interfaces. We will use this. But if we have a way to access this quantity, we can really understand the mechanisms that are behind the thermal behavior, the Cp behavior of the nanomaterials. But then if you use this, you can also determine under which conditions that your system should show an increase or a decrease of your system. Increase or decrease of your system, theoretically, one can say, okay, I am showing positive deviation from the ideal behavior. This is the usual theoretical way. It is also done, this is the way which is done with the Henry law with respect to the Raoult law, but also experimentalists like to draw the result and saying the deviation of the heat capacity of the nanomaterial with respect to the heat capacity of just of the suspending material, so that you also in this case you can understand the condition with which you can have positive deviation. But then let's see. Now we need many inputs to do this calculation and to see the various terms how they will change in order to understand the physics behind this kind of suspensions. You see that you need the Cp of the suspending material, Cp of the nanoparticle, the diameter. It's the density of the nanoparticle. And then you see some experimental results. The green line is the Cp of the KNO3, the suspending material. Then these vertical lines are signaling that this one on the more to the right is the Cp of, there is a transition solid to liquid, here is solid transition. The other lines here is the Cp of the suspending material. So then we need all this quantity, also from the point of view of simulation, if we want really to to proceed with the process of understanding. So then we construct the molecular dynamics. I will not comment on the modeling. I want simply to show that during this analysis, now we are using two groups, we can say, of materials. One is correspond to really the silica in KNO3, but then also we are using a different material that in which we have a different kind of microscopic interaction between the nanoparticle and the suspending material. That means in all these cases studied experimentally, essentially they are just studying one system. We can say system in which you have attraction plus repulsion between the nanoparticle and the suspending material, but instead now we are also going to study case in which we have just repulsion between the nanoparticle and the suspending material. So then what is the molecular dynamic strategy? You have first to evaluate the CP of the nanoparticle, then you have to evaluate the CP of the suspending medium, then you have to put the nanoparticle within the suspending medium, and then you have to evaluate the CP of the nanomaterial. This is a snapshot of the nanoparticle, silicon nanoparticle inside KNO3. It's a snapshot of the silicon nanoparticle in liquid KNO3, and then you have to extract some information for all the trajectories that are generated from the molecular dynamics, and in particular you have to concentrate your attention on the so-called density profile, how the density is structured around the nanoparticle. Okay, so then, but before going to really to study suspension, I want to make really to show to you some result on the nanoparticle alone, because by themselves, they have a lot of interest. Then you see the results of a nanoparticle that is crystalline inside. And this is, we can say, is a FCC structure of a nanoparticle, a nanosphere. And here on the right, you have a density profile of a nanoparticle that inside is amorphous. And this is model, it's an amorphous that is a model for amorphous carbon, imagine. So, but then you see that from these two pictures that there is a restructuring of the surface of the nanoparticle, and the restructuring is different in these two cases. In one case of the nanoparticle, we say the crystal nanoparticles, we have around the surface, you have a decrease essentially of the density of your nanoparticle. There is a region that we can say interface. The gray region is the bulk phase. In this interface, there is then that of the bulk. Instead, if in the other case, you have this interface region as a density is larger. So this means that we can expect also a different thermal behavior, because then the thermal behavior, these are solid objects. Solid object, you know that this is controlled by the phonon, the way in which the atoms are vibrating. So maybe this will vibrate in a different way from the bulk, and also this, but then maybe the effect is the opposite in these two cases. And then we see what is the CP variation of this nanoparticle. And then you see here, we have the specific heat of the crystal nanosphere, and here the CP opla of the CP variation of the amorphous carbon. But I mean, there is a lot of saying. I mean, the smaller particle have a much larger, a much larger heat capacity. When you increase, what is this important? When you increase the nanoparticle size, then the heat capacity is going to the heat capacity of the bulk material. So this is in black written there, and also there is a region in which the heat capacity coincide with that of the bulk. But all these findings are coherent with the appearance of softer interface phonon in this case, for the crystalline case, that is bringing to an enhancement, because it's more liquid-like, and liquids, the surface is more liquid-like, and liquids have a larger heat capacity than solid. So, but then in this other case, in the case of amorphous carbon, we can say, which is density is higher, then the surface photon are harder. So then essentially there is no increase in the capacity. So then we can say already we can explain something on the basis of phonon theory. But then also the thing that that is also interesting in the nanoparticle is the phase transition. And here in this two animation, you see that somehow one can look at the phase transition with these flying particle methods. We reach a temperature in which from the quasi-liquid layer on the surface of the nano object, I mean, particles are starting to be ejected. Then if you increase a little bit the temperature, then many particles will leave the particle, and essentially the particle will do a phase transition. But what is why I'm saying this? But in this case, now you can try to evaluate the melting temperature of the nano objects, I mean, of this crystalline nanoparticle and for the amorphous nanoparticle. And you see that they are the collection of the melting. Now, this case are both for crystalline, but for nanoslab, for nanosphere. But then you see that they are the temperature of melting against the thickness, temperature of melting against the diameter of the nanoparticle. They are approaching a value of melting value. But then you see if you make the same plot in which you put in the ordinate, we can say the ratio between the surface atom with the total atom, you see that these appear linear when you go to low temperature, and this melting temperature is not approaching at all the bulk melting temperature of the corresponding bulk material. So you see there are some properties that are going to approach the bulk value, but some other quantities are never approaching. And this is also clarifying the understanding somehow of the melting process, if the melting process is some process is driven by surface or not. But this means that in this research, melting process is a process that is guided by surface, as maybe the engineers, they know much better than physicists. Okay, so then after this, now let's go to our nanomaterials, in which now we have our nanoparticle in this salt. Let's examine first the case in which you have the nanoparticle in the solid salt, KNO3. Let's examine the result for silica sphere in KNO3, silica slab, and amorphous carbon sphere, always in the nano, in the suspending solid KNO3 and in the solid KNO3. But then what do we observe here? That always the excess term that we were defining in the chemical physics approach is always positive. So this means that there will be always the CP of the nanomaterial will be always larger than the CP of the ideal term. There will be always a positive deviation for this. But then let's see that now, when we draw the variation of the CP in according to the chemical physics model, we see these points are the points that correspond to the simulation, and these lines are the lines that correspond to the theory. Then you see for the silica nanoparticle sphere in KNO3 solid, and this is now the enhancement according to the way in which the experimentals are defined. There is always an increase of the CP of the nanomaterial, of the solid nanomaterial. Then you see for the nanosphere, for the nanoslab, and also for the amorphous carbon sphere in always KNO3. And then you see in this case, if you see the scale, the enhancement is much larger than the case of silica in the silica particle in KNO3. How we can understand these things? So now let's draw this density profile of KNO3 around the silica particle. This line here is the silica particle, and these are the density profile of KNO3. What is happening to the structure of the solid KNO3 close to the nanoparticle? That there will be a region, an extended region, in which, in which the density of the solid is much lower than the density of the bulk solid. So this means that the surface of the KNO3 now that has lower density is characterized by surface phonon that are softer than, we can say, than bulk phonon, but this is known that this region will give a much higher contribution. So that's the physical reason for which we have always this increase. And then also you see that it depends also from the temperature. This is light dependent from temperature. Then let's move on. Also you get, this is the results in which now you have for the silica in amorphous carbon. You see that now also here there will be, oh my God, there will be a decrease, already 45 minutes are over. Okay, there will be a decrease already, but I mean, there is also a region of excluded volume. So if since there is repulsion, then also the particle, the nanoparticle, will vibrate in this case. So this is also one of the thermal modes that give contribution to this, and that's for this reason that you can have a larger contribution with respect to the case of the silica. I will skip this part here. Then also you have the same kind of behavior, essentially. If you take just the KNO3 with holes, then also you see that if you have just holes, empty cavities, then also they are close to the cavity, then the density of KNO3 is decreasing. And then also in this case, you are expecting an enhancement due to the fact that now these phonons that correspond to the particles that stay in this layer are much softer. They vibrate in a different way from the phonons of the bulk, and then they will contribute in a positive way to this. Now let's go to the liquid, and then in 5 minutes we will approach the conclusion. So then, the case of the liquid, we will see something that is a little bit different from the case of the solid, that for the case of silica sphere, in which, remember, we have attraction and repulsion with the suspending medium, is different from the case of the amorphous carbon sphere, because the the exotherm in this case is negative for silica, but is continue to stay positive for the amorphous carbon. This means that most probably in one case there will be a decrease of the enhancement, in the other case there would be an increase of the enhancement. That means an increase of the CP of the nanomaterial with respect to the suspending material. And then you see here the result, when if the red lines are the ideal contribution, something that corresponds to Raoult law, and then these other lines that are something that correspond to the Henry law for the suspension, you see that these are all negative. So there would be a decrease on the heat capacity of the nanomaterial. Instead, for the case of amorphous carbon, you still continue to have an increase in heat capacity. Why this? Can we explain this on the same basis like we made for the solid? To do this, you need, if you want to explain the same basis, you need a phonon theory for the liquid. I mean, phonon theory for the liquids is something that is just developing now, although the first idea were presented by Frankel in 1946. But I mean, based on a sort of caging effects, because also in a liquid, you can say due to a caging effect, particle first will vibrate inside the cage as a solid around the lattice position, but then they will jump and they will take a diffusional motion that is typical of a liquid. So then also to make the life shorter to you. Also in the liquid, you can build, we can say, a phonon theory. I will not go through the details of this, but I will just remember that this can be associated to a caging effect in the liquid. If your liquid is more, we can say, structured, that the caging effects is more strong, is very strong, then we can say there will be more vibration of the particle inside the cage. So then we can say that there are harder phonons, phonons that correspond are more similar to the case of solid. When the caging effect is very low, then the particle can move. So then we have just diffusional motion. Then we can say the liquid phonon are much softer. Just remember this, skip all this, and then let's go to examine our results for the liquid. Now, what do we see in the case of silica in liquid KNO3? Remember that we were finding a negative value, a decrease of the heat capacity. But what do we see from the density profile? That due to the attraction, now the attraction is, in case of the liquid, the solid was not enough to pile up the atoms in close to the surface, but now in the liquid phase, the attraction is such that KNO3 will construct really layers of KNO3 around the nanoparticle. But if in these layers, if this more structure, in this layer somehow many particles are forced to stay in this layer. They cannot escape it easily from the layer. So this means that they have harder liquid phonons in this region, with that are phonons, liquid phonons that are much harder than the phonon that stay in the bulk liquid. So that's the reason for which now the CP is decreasing, because harder phonons are less they contribute to the CP now. And in the case instead of amorphous carbon, what you see, there is repulsion. Then there is a repulsion. It's impossible to build a layer, but you see that the density of KNO3 close to the is lower than the density of the KNO3 in the bulk. So that means that the phonons that stay in the layer around the particles that stay around can move much more easily. So then the phonons are softer, then they will contribute in a positive way to the CP, and that's the reason for which you have an enhancement. So conclusions such that then heat capacity is in the solid phase, there would be always an increase of the specific heat due to the surface solid phonons that are always more liquid-like than in the bulk. In the liquid phase, the system in which have attraction part in the potential, they show a decrease in the specific heat. Instead, one that you have repulsion, we can have attraction, and then finally with criteria, can we extract this criteria? Yes, because in the solid phase, then lighter particle, you have always an increase, but lighter particle will make a larger contribution, smaller particle will make a larger contribute, and the spherical particle, although I was not comparing, the spherical nanoparticle will give larger contribution than platelet kind of nanoparticle. Instead of liquid phase, if you want to construct a nanomaterial with very high heat capacity, then you have to use system which there will be a repulsion from the nanoparticle and the suspending medium. And so once more, also in this case, lighter particle will generate lighter heat capacity. And once more, also this, for the nanoparticle, nanosphere are better than a nanoproton. And with this, I'm closing my presentation. And thanks for your attention. Now we can have discussion.
Thank you very much, Dr. Bruno, for
Thanks
the
a lot
nice
for
presentation. We'll give you a virtual round of applause. Appreciate your time.
Thanks.
At this point, we can open it up for questions or comments from our colleagues at Binghamton University or at VIT? Since we have a manageable group, please feel free to unmute yourself and ask the question.
Hello, sir.
Was clear.
Yes.
Hello, sir. Myself, Prem Kumar, sir. So what are the materials used for heat transfer fluids, sir? For heat transfer fluid passage. So what are the materials they are using? Sir?
Yeah.
Containment materials for storage of the salt.
I have the thing that I was showing to you primarily is for the heat storage material, okay? To store it, because then the materials that are used, that on which I am showing the results, are these, we can say, nitrates, potassium nitrates. Then with the results with sodium nitrate will be quantitatively a little bit different, but not qualitatively different. But then also the results for the solar salt will be not different. Now I am just using silica. I was using silica nanoparticle and we can say amorphous carbon nanoparticle. In all the application, technological application, just solar salt is used. But then you understand here that if we are able to build a material that will be, I mean, just by exaggerating to give to you a more clear idea, that has the 50% more on heat capacity, then you can have a storage that is half of the one that are used now, and you can use half of the material that is used now. So then you understand really why it's much more convenient to build such kind of system.
Okay, sir. Thank you so much, sir.
No problem. You're welcome.
Okay, sir. Thank you, sir. Thank you.
Thank you. Thank you, Mr. Kumar. Any other questions?
Yes, I want to ask about the conductivity, the thermal conductivity with the addition of these materials.
Yeah, of course. I was just, I mean, you are right. I was just presenting specific heat capacity. Then, well, let's comment also on the heat conductivity of this kind of material. The heat conductivity is, we can say, is always, we can increase the heat conductivity by using this material. Why in general, you can use, and also from the experimental point of view, in general, the results that the people are getting are much more stable than with respect to the one that I was showing in the specific, for the specific heat. Why in general there will be a much higher conductivity in this material? Because you are introducing in your system more degree of freedom, more thermal modes, we can say, that are, I mean, all the game is here is really to create thermal modes that can be excited thermically. In the case of the heat conductivity, thermal conductivity. So then the problem is that, I mean, these are in the liquid, let me go to show in the liquid phase. Okay, let me go to show that there is also, okay, here, there is, you see that the particle, although we were confined by the time scale of the solvent, we were not exploiting a little more about the time scale of the Brownian motion. But there will be a Brownian motion. So then together with the Brownian motion of the particle will, and then also around the particle there is the layering. So then essentially you have a larger particle that is moving, and then there will be density waves also that will be developed inside the liquid. So then will be also a setup of hydrodynamics kind of interactions. So then for all these kind of reasons, then the transport will be larger in the case of this whenever you introduce nanoparticle in your system. It's a combination, but largely dominated by the Brownian motion and by the hydrodynamic interaction, the hydrodynamic modes, density waves that are created inside your system that can help in transport it. I hope that I was clear.
Mm.
Okay.
Thank you.
No problem. Welcome.
We also have a question in the chat from Subankar Sen. The question is about if you can explain what does the experimental dilute regime mean?
Okay.
Clarify how much are the experimental and theoretical dilute regimes differ?
Okay, so then I will say that this is a question. I have to say, maybe then I have that, maybe he's referring of some papers that were published. I am joking. So then, because it's precisely a question that one referee of one of our papers is asking, what is the dilute regime? What means dilute regime? Of course, dilute regime in a suspension, when I was, let's go back to the case of solutions. Dilute regime, you see here, and also in this picture, in the way in which is defined dilute regime one here, if you see in this region, is that, I mean, the solution is really, in this case, is following the route law. So then we can say that it's a dilute regime because it's really following the route law, and that route law means that there is no interaction between the particles. By the way, this is the route law. This means route law. So if there is no interaction between particles, that means the system is ideal. So the particles, they do not interact. At any length scale, they are not interacting. So then, in the case of the Henry law, what means that now still there is a regime in which property they change linearly, but with a different slope with respect to the route law. That means that some non-ideality is present in your solution, but still the particles, the solution property are changing linearly. What does means this? That in this regime means that the non-ideality, now think to our system, the non-ideality is set up by the fact that there are layer regions, surface interface regions around the nanoparticle. But still the system, by changing the density inside this regime, behaves, we can say, in a linear fashion. Why it behaves in a linear fashion? Because still in this regime, the nanoparticles are non-interacting, because to interact, the nanoparticle, I mean, they have to reach a certain concentration. And so that means the G of R of the nanoparticle is still, we stay at is largely 1. We can say there is no peak in the G of R in the pair distribution function of the nanoparticle. So then essentially this is the meaning. And also do not forget that in the linear regime, so the solutions are stable, but also the nanoparticle mixtures, we can say, have to be stable. So then as not, I mean, to stay aggregation of the nanoparticle, in which then if there is aggregation, then the number of particles in your system is changing. So then you cannot define, you cannot define thermodynamic quantity. But you can see that's the way in which the dilute regime is defined in the same way in which it is defined there. So there is a regime in which essentially the nanoparticle interaction as a G of R that is virtually equal to 1, like in a gas phase, for example. But then think that there is no theory that say that is defining the dilute regime for all the kind of system. Dilute regime is specific, something that is really specific for a specific system. Okay. I hope that I was clear.
Okay, great. Yeah, Subhankar sends us that clears things. So he's very satisfied with the answer. Thank
Okay. But then I will please ask him to get in contact with me. I would like to continue the discussion with him.
Okay, okay, great. Yeah, yeah. So, yeah, he confirmed that he will definitely be in touch with you.
Okay, okay, good, very nice.
Yes, thank you. Any other questions from our colleagues at VIT or Binghamton? Okay, great. So if there are no questions, I'd like to, again, on behalf of VIT and Binghamton University, thank our distinguished speaker, Dr. Bruno, for joining us all the way from Italy to deliver this presentation. We are definitely delighted to have you part of this webinar series, and thank you for all your contributions. And I'd like to thank you again for everyone that participated and asked questions, and very interesting questions that led to very serious discussion. So again, thank you very much, Dr. Bruno, for joining us. And
thanks to you, to all of you.
Thank you, thank you, thank you very much. So at this point, I would like to conclude the webinar series. But before we conclude, I would like to let you know that we will be sending a follow-up after later today with the recording for this presentation. So if you think this would be of interest to any of your colleagues, any of your students, please feel free to share the recording with your colleagues. I would also like to take this opportunity to again invite you to join us next week for our continuation of this webinar series. As you can see on the screen, next week we will have Dr. Fu Danning, who is an assistant professor of system science and industrial engineering in the Thomas J. Watson College of Engineering and Applied Science, who will talk about his research in the area of additive manufacturing of metal parts with complex structures. So please join us next week. It's the same registration link as you have seen. Registration only takes about 15 to 30 seconds, so it's fairly quick. So thank you again for joining us today and for participating in this webinar series, and look forward to seeing everyone next week. Thank you. Have a good evening in Italy and India, and enjoy the rest of the day if you are here in the US. Thank you again, Dr. Bruno. It was very nice to meet you.
Yeah. Bye-bye to everybody. Bye-bye.
Thank you, sir.
Thank you.